plate tectonics is the unifying theory for the earth sciences. So what do we mean by unifying theory? Well, unifying theory is something that helps explain the wide variety of processes and phenomenon in a discipline, in a field of some sort. In biology, it might be DNA or evolution. In chemistry, it's atomic theory. Some disciplines are still seeking a unifying theory. So in physics, trying to unify quantum physics with Newtonian physics is something that has continuing to be sought. But in the earth sciences, plate tectonics seems to be that unifying theory that can bring together the observations of a lot of the phenomenon on Earth. So before we jump into plate tectonics, let's think about the refresher about the Earth's surface or the Earth's structure. Remember that the Earth can be divided into two different types of layering. One is a compositional layering, where the crust is a different composition than the mantle, which is a different composition than the core. We can also look at the layers of the Earth in terms of how they respond to stress. So are they strong and solid? Are they deformable? So the lithosphere is strong and solid. The asthenosphere is more plastic. It's solid, but it can deform easily. The outer core is molten and the inner core is solid again. So when we talk about plate tectonics, we're thinking about both the compositional and the structural, the response to stress ways of considering the layers of the Earth. So a tectonic plate is made up of the crust, which is a compositional layer, the continental crust and the oceanic crust, plus the lithosphere, that top part of the mantle that is brittle, that's strong. And it sits on top of the plastic asthenosphere that isn't molten. It's just solid and deforming. So what exactly is plate tectonic theory? Well, the idea is that we have plates that make up the surface of the Earth that ride on the asthenosphere, and these plates will interact based on how quickly they move, the angles of those interactions, and the composition of the plates. So how two oceanic plates that collide will behave differently than an oceanic plate and a continental plate. Plates that are moving much faster, you can see in the Pacific, plates are moving much faster than in the Atlantic. So the ways that they interact, the angles in which they interact, and the composition all play into the types of boundaries we have between them all. Now, plate tectonic theory is, it's only been really accepted in the field for about maybe the last 50 or 60 years. But the concept of tectonics has been around for, or at least the idea that the Earth's surface might be in constant change and motion is something that has been recognized, at least suggested, for quite a while. Now, we can go back to Ben Franklin. He is a very interesting character, both good and bad. But he suggested in 1782 that looking at the surface of the Earth and how the things that he sees happening, he explained that such changes in the superficial parts of the globe seemed to me unlikely to happen if the Earth was solid to the center. So at the time, the idea was the Earth was solid to the center and the surface of the Earth didn't change since creation. Ben was suggesting instead that he didn't think that was likely. Instead, he imagined that there was a fluid inside the Earth, a very dense fluid, and that the plates on the surface of the Earth would move like a broken shell on that fluid and create because of the violent movement of the fluid itself. Now, obviously, he was off on a lot of things, right? It's not a thick fluid, but it's rather the deformable mantle. But he at least started to hint at the idea that maybe the surface of the Earth was not a static thing, but rather something that changed over time. By the middle of the 1800s, there's more evidence. So Thomas Seuss had noticed that when you started to look at the distribution of different types of fossils, you found things on different continents, fossils in different continents from organisms that were not crossing the oceans that exist today. So different types of organisms like plants or small mammals or small dinosaurs, things that would not be swimming across the Atlantic, could be found in South America and Africa, or Africa and India, which suggested to him that all of these plates were in fact all together at one point. He referred to this conglomeration of plates, the first sort of idea of a supercontinent, as Gondwana, based on this fossil evidence. So much like William Smith looked at fossils to correlate different layers of rock, Seuss did the same thing, just saying that this correlation means that these plates had to have been together at some point. By the time the 20th century hit, we had the first real suggestion or proposal of how this might work. And it was actually brought to the discipline not by a geologist, but by a meteorologist. So a fellow by the name of Alfred Wegener, who is a meteorologist, wrote a book in 1912 called The Origin of Continents and Oceans, where he proposed this model of continental drift, where the continents were once together and then they have moved apart. And they're constantly in motion based on looking at things like fossil correlation and the fact that the edges of continents seem to fit together. He was onto something. And his maps in this figure here show how different South America and Africa seem to fit together, except that the science at the time would suggest otherwise. And it was because Wegener wasn't a geologist and was somewhat outside of the mainstream. The American Philosophical Society, which is very much the science society of the time, remember we talked about science as being referred to as natural philosophy, referred to The Origin of the Continents and Ocean, the book, as utter damned rot, and anyone who valued his reputation for scientific sanity would never dare support such a theory. Which is somewhat unfair, but which is also, you need to have evidence to prove such a theory. And Wegener had pieces of it, but not all of it. And much like we've talked about this week with misinformation or inaccurate science, you always have to be careful when some sort of dramatic new theory is put out there that there's the evidence to support it. Now, Wegener would not live to see his theory become accepted, but over the next 100 years, a lot of pieces of evidence were collected to support his theory. So the first step is kind of after World War II, when the Cold War was really picking up. And during the Cold War between the U.S., the West, and the Soviet Union, one of the most important things was keeping track of submarines. Now, submarines can be pretty stealthy. They can carry a lot of weapons. And the U.S. was very interested in finding where the Soviet submarines might be. And in order to do that, you really needed to have an accurate, hyper-accurate map of the sea floor. So the U.S. Navy, under the auspices of scientific research, had folks go out there and map in great detail the ocean floor, especially the North Atlantic. This is headed by a few scientists by the name of Harry Hess and Robert Deitz. And they were able to construct a theory of what was going on in the ocean floor. But what was required was a couple pieces of information. One of them was the actual maps of the sea floor, and those were developed by Marie Tharp. Her quote is quite telling. So she said that, "I had a blank canvas to fill with extraordinary possibilities, a fascinating jigsaw to piece together, mapping the world's vast hidden seafloor. It was a once in a lifetime, a once in the history of the world opportunity for everyone, but especially for a woman in the 1940s. The nature of the times, the state of the science, the events, large and small, logical and illogical, combined to make it all happen." So what Marie Tharp is suggesting here is that although the auspices for why the mapping was done, for the Cold War purposes, it ended up unlocking a vital piece of information for understanding how the planet worked. So the map that you see on the left is developed from Marie's original mapping of the sea floor that they did with boats using sonar. And they also mapped the sea floor magnetically to see see how it changed. And why they did it magnetically, one of the reasons, or one of the fallouts here, was that geologic material can preserve the magnetic characteristics when that material formed. So a mineral like magnetite, when it forms, will align with Earth's magnetic field. And it will give you kind of two pieces of information. One of them is whether the Earth's magnetic field was normal, which is what we have today, where if you hold a compass, the arrow points north, or if it was reversed. So sometimes the Earth's magnetic field flips polarity. So your compass needle, the north, would actually point south. We're not quite sure exactly why this happens, but it happens frequently in Earth's history. And also the rocks can retain information about the location of the North Pole relative to where those rocks were forming. So we call this whole field of studying rock magnetism in the past as paleomagnetism. And if we have information about the timing of some of these events, the changes of polarity and such, we can use the polarity of rocks to correlate them, to tell time, and to tell us something about their prior locations. Now, the Earth's magnetic field is definitely not a constant thing. There's what we call polar wander, where the Earth's magnetic pole actually moves. And sometimes it's a fairly regular motion, and sometimes it can speed up and get unpredictable. And sometimes the whole polarity will flip, like I mentioned. So if we look on the left here, this is a map showing how the Earth's magnetic North Pole has shifted from 1831 to 2007. And then on the figure in the lower right is how many kilometers per year the pole moved. And you can see that from 1590 to about 1970, it moved, but it was didn't move a lot sometimes, and it might have been up to 15 kilometers per year. It's fairly stationary. But then since 1970, the polar shift has picked up, sometimes moving 50, 60, 70, 80 kilometers per year. We're not entirely sure why, but it's part of our fluctuating magnetic field. So when Hess and Deitz and Tharp went and mapped the ocean floor, they looked at the physical features of the ocean floor and also the magnetic characteristics. And what they found was that the remnant polarity of the magnetic field is preserved as stripes on the ocean floor. They're not visible, obviously, but they are seen in the magnetic characteristics of the rocks. And that when you started at the mid-ocean ridge, like you see in the picture on the left, the stripes were the same on each side, which to Hess and Deitz suggested that you had seafloor spreading. So lava erupts, it gets the flavor, the polarity of whatever was happening in the magnetic field at the time, and then it gets pushed to the side. So this piece of evidence of the magnetic striping of the ocean floor was the first to really suggest that we were creating new ocean floor at the Mid-Atlantic Ridge and other ridges. You can see on the figure on the right is a list, or is a figure that shows how the magnetic field has gone from white, which is normal, to black, which is reverse over the last 140 million years. So it flips back and forth. It doesn't flip on any sort of regular cycle, but we can sample rocks that have these different polarities and date them and create this chronology of Earth's changing magnetic field. So if we know something about the dates of the rocks, and based on their polarity and the distance from the mid-ocean ridge, we can calculate how fast that ridge is spreading. The other way we can look at this is just the age of the seafloor rocks. So we looked at this in class, but the seafloor will have different ages, and we can date them, and then the distance from that mid-ocean ridge will give us the rates of motion. So the youngest seafloor rocks are 0 years. They're forming right now, even as we speak. The oldest can get up to a couple 100 million years old. 220 million is the oldest. It's a little, I think it's not really shown on this map, but some of the oldest we have now is 220 million years old. So when Hess and Deitz suggested that seafloor spreading was creating new ocean crust, the biggest question people had is, we know the Earth is old. where is all of that material going, right? Because if it didn't go anywhere, the Earth should be getting bigger, and it's not. So one of the outstanding questions with this next piece of evidence about tectonics was what was happening to all that crust. Another way that we saw evidence of plate motion was in what we call hotspots. Hotspots are plumes of hot mantle material, not liquid, but hot rock that rises up from maybe the core mantle boundary. And when it reaches the boundary between the asthenosphere and the lithosphere, it would start to melt. We'll talk about why in the next unit. But it would start to melt, and kind of like holding a candle underneath a piece of paper and then moving the piece of paper, you can burn a track through that paper. The mantle plume and the magma that it forms would make a track on the plate that was moving over it. The plume stays still, and the plate moves over it, and you create this track. So on the left is the Hawaiian Emperor Seamount chain, which is a hotspot track. You go back 60 million years in the northwest of Hawaii, you get to Suiko Seamount. That is part of this chain, and that formed 60 million years ago, and the Pacific Plate has moved that distance and direction in the last 60 million years. And then the youngest stuff is things like at Kilauea and Lauihi on the Big Island of Hawaii that represent the current location of the Pacific Plate sitting over the Hawaiian plume. So we had that information about, plates seem to be in motion. Now, what do we need to know to figure out the nature of the boundaries? Well, one of them is to think about the earthquake data we looked at. Some of the earthquakes are shallow, some of them are deep. So if we look at something like the Mid-Atlantic Ridge, it's all red dots, which are shallow earthquakes. And that suggests that we have something going on that's mostly shallow. So we'll talk about the types of boundaries in the next video, but in the lower right-hand corner is a divergent boundary, like a mid-ocean ridge, where the earthquakes are happening just up near the surface, within the first few kilometers. Someplace where a plate is being consumed, so we're now getting rid of the plates that were being created. We see earthquakes that get deeper and deeper as that plate gets shoved back into the mantle. So you look at the Andes, or Japan, where you have green and blue dots that represent deeper and deeper earthquakes. They are, like the picture in the top right, a subduction zone where you have some shallow earthquakes, but then they get deeper and deeper as you start to shove that material back into the mantle. So these earthquakes, not only do they tell us something about the nature of the plates, but they tell us something about the location of the boundaries. We can also look at volcanoes to tell us something about the nature of the boundaries, where they are, because you can see the blue dots on here, the red dots on here. The volcanoes, many of them follow the plate boundaries. And what we'll find out is that the style of volcanism at these different volcanoes can also betray what's going on at the plate boundary. Volcanoes forming in places where plates are moving apart end up being different than volcanoes forming at places where one plate is being shoved underneath the other. So we have all of these various lines of evidence. We have earthquakes and volcanoes, the age of the seafloor, its magnetic striping, the topography of the seafloor, the location of fossils. We have the correlation of the shapes of coastlines. We have all of these bits of information that were swirling around. And then a fellow by the name of J. Tuzo Wilson began to really put together all of these pieces of information and defined sort of the three main types of plate boundaries. And that's what we'll get into the next video. But to give you the preview here, there are divergent boundaries where plates are moving apart, things like a mid-ocean ridge or continental rift. There are convergent boundaries where the plates are pushing together, they're colliding. That might be a subduction zone or continental collision. And then we have places where plates are moving side by side. So we have what we call a transform boundary. And J. Tuzo Wilson was able to sort of define how plates would interact. And then we can sort of look at sets of processes that happen at these different boundaries that mark the evidence that combine the evidence that we have for tectonics and the processes that occur at each of these different types of plate boundaries.